60 seconds and we're back online. So just a reminder, we will stop at 1:40. And I have the tissues up here because you do remember this is our last Saturday class. Tough moment.
What page again?
6:44. Okay, I'd like to resume. We're working on page 644, section 11.6, going over the assigned homework problems. Most of these we can do orally. So, Tony, can you get us started with number 2?
12 over 13.
Wait a minute, let me know if you object or want to say some more about it. Hannah, 3.
3 over 4.
Good. And 5, please, Freddie.
9 over 13.
We want 10 over 13. There's some dispute over this because the picture cards are Jack, Queen, King.
Oh.
That's just definition, not a big deal. And 6, please, Freddie, redemption.
25 over 26.
That's right, we want 23 over 26 because the picture cards again are Jack, Queen, King. You're probably counting the aces. That's not standard. Okay, so we go to number 7. And please note they want the probability of not being dealt this type of hand. So, Tony, your answer to 7 is?
99.99%.
Okay, and your answer to 9, please, Hannah, is?
99.8%.
All in favor? And do you have 10, Freddie?
I had like 99%. I had like 999 over 1,000, like 99%.
Yeah, but we need more decimal places next time you do it. Because,
I had 51 or 08 divided by 2598960. Subtracted from 1.
perfect, okay, that's enough. You know how to do it, that's all I'm really concerned with. Number 12, please, Tony. A
For A, I have 0.78,
and B.
0.22.
Any thoughts? Okay, 13, please, Hannah.
0.82.
All in favor? Differences? Okay, let me get to what I need to do. Chapter 11.6.
I have the same thing, I just had it as a fraction.
Okay.
21 over 118, or 1 minus 21 over 118.
How did you do it?
Yeah. Yes. that
1
was-
minus 21 over 118, and then I just converted it to a decimal per instructor.
This simple.
Oh, no, simplified fraction, my bad.
Okay, so Freddie, did you see the approach?
Hold up. 13. Why did I put like 97 divided by 118. Why did I do that?
You asking
That's what I
me
have.
why you did that?
I'm asking myself why did I do that? I'm asking myself why did I do that?
But that's right,
Huh?
that's correct.
97 divided by 118
Yes.
equals
Perfect.
97 over 118.
Just a calculator problem then. Nice work.
Okay.
You did the probability. So 14, and Freddie, what you have for 14?
52 over 59.
Perfect, it's a winner, you understand this stuff easily. And 15, please, Tony.
I have 47 over 59.
So I got
47 over 59, we have winners there. And 17, please, Hannah.
2 over 13.
Good?
Yes.
And 21, please, Freddie.
1 over 26.
We have winners. And 23, please, Tony.
9 over 22.
Yep.
Good. And 25, please, Hannah.
5-6.
And 26, please, Freddie.
4-6, to 2/3.
Perfect. 31, please, Tony.
3/4.
33, please, Hannah.
5/8.
You guys take this course before? 34, please, Freddie.
3/4.
Awesome. 35, please, Tony.
33 over 40.
All in favor?
Yes.
Nice work. And 37, please, Hannah.
4 over 5.
39, please, Freddie.
7/10. 7 over 10.
We have a winner. And 41, please. This one has an English problem, so don't feel bad if we don't have agreement. It's just the way the problem is worded. 41, please, Tony.
43 over 58.
That's the sort for answer.
That's what I got.
Okay, good. And 42, please, Hannah.
1 over 6.
45, please, Freddie.
113 over 174.
No, this might be the English problem. Has completed less than 4 years of high school. How many have completed less than 4 years of high school? I get 29, agreed?
We're doing
40.
45.
45, okay, I'm in the wrong place. So, I withdraw everything.
4 years of high school.
And your answer one more time for 45 is?
113 over 174.
And you're absolutely right, I'm doing the wrong problem. I gotta work on my 4s and 5s. Okay, and we now advance to 46, please, Tony,
117 over 174.
which,
Oh,
no, that's 45, you're doing the wrong problem too.
That's what I get for 46.
The same number?
174
Oh.
for 46.
Do it 113 over 174?
No, 117 over 174 for 46. That's what I got.
Will it reduce
Yes.
to,
39 over 58.
okay, partial credit, guys. It does reduce. And 49, please, Hannah.
43 over 69.
43 over 69, a fairly hard problem. Freddie, do you get the same, 43?
For 49,
49, yes.
I got 409 over 669. Is that reducible? I mean, I calculated it and reduced that.
Hannah, you said 43 over 69?
Yeah.
I have that too.
Yes,
Because the
but where did it
calculation-
come from as a raw number before you reduced it?
Oh, 860 over 1380.
Yeah.
Okay, so Freddie,
Oh, I got that one wrong then.
it's not in the Army. So count up all the people that are not in the Army off the graph. 280 plus 60 plus 170 plus 10 plus 290 plus 50, agreed? And you're given a total of 1380. I don't have my sign yet, but the probability of A is the number favorable over the number of total. Okay, so it's a matter of graph reading,
I gotta go back to that one.
okay?
See what I did wrong.
And we go to 51, please, Hannah.
1240 over 1380, which reduces to, reduction from, give me a second, it says reduce.
We take the second.
Over
We
69.
have a winner.
1240 over 1338, right, was the first one you got?
1380, but yeah,
1380?
yeah.
Okay.
Okay, we know how to do them.
So what was your answer again?
62 over 69. We're talking about 51, right?
Yeah.
Yeah.
Okay.
Okay, great, gold. And Tony, take us out of 53.
26 over 69.
26 over 59, all in favor?
Or 69.
69, 26 over 69, all in favor?
No, I got 260 over 669.
Is that what you guys had earlier?
No, I have 280 plus 60 plus 170 plus 10 over
Oh.
1380.
Mhm.
And then that equals 520 over 1380.
Alright, I need to go back to see what I did wrong
Okay,
with
we'll
that.
check those out. Now we go to the handouts, page 187.
Full disclosure, I don't have all of these done.
Pardon me, ma'am?
I said full disclosure, I do not have all of these done.
Neither do you.
187,
Some of them were unreadable.
yeah.
I did the ones I could read, the ones that were cut off.
911, they got a lot of excuses, what should I do?
The ones I was able to figure out reading, I
Do I hear a little bit of emotion in your voice? They're the ones I was able to read.
So 5, 6, 7.
It's valid, it's valid. So we're looking at page 187 and we're looking for a number 3 through 10.
Where am I?
Hmm.
187.
It was on the first probability handout he gave
No,
me.
it's on that first handout earlier. It's on the previous sheet. So we have one that we got last week.
Oh, okay, yeah, I got it. I was only able to see 5, 6, 7. Yeah, 5, 6, 7.
Okay, so what do you have for 5?
I got
Ready?
11, 19.
Do we have agreement?
Yes.
11?
11 over 19 for number 5. If I saw that, it looked like a 5 in front of the word computer. It's barely readable, so.
Sorry about that. Okay,
Is that right? 11 over 19? Number
12,
5?
but I'm gonna just.
I can't read 5. We'll skip it, okay? Oh, no, we sort of can read it, not really well enough. And I can't read 6, I can't read 7, I can't read 8. Can anyone read any of those? I can
I
read
did.
10.
Seven.
I
You
tried
did
to do
7?
6 and 7,
Yeah.
yeah, I did
Oh,
7.
Tony, Freddie, what'd you get for 6?
6 I got, I read it as 10, 17, 10 over 17 plus 7 over 17 equals 17 over 17
All in
equals
favor?
1.
Well,
From
it's
what I
missing
can-
the number of Plymouths.
Yeah, I didn't know.
The number of Plymouths is cut off.
Number of Plymouths is missing, so it can't do the problem. Let's go straight to 10. Single card, what's the probability of a 4 or a diamond? 10A, a 4 or a diamond. Well, how many diamonds are there? And how many 4s haven't you counted yet? Everyone have find number 10 there?
Oh, I have, yeah, I didn't know. Were you asking someone specific? Okay.
187, 3 through 10, so 10 is the only readable problem.
So for 8, I have 413.
413, all in favor? Okay, Tony B
1 half.
and Tony C,
I haven't done this one yet, but a jack, so.
or a black card.
So, sorry. 6 plus 29 over 50.
28, 28, 28,
Oh, yes.
28. 28, Nana, for 10C, 28 over 52? Okay, good. Okay, so now 188 is maybe a little bit more readable. Actually, it has to be, everything's more readable than that. And some of these are fun. So what we want is number 11. Okay, so Freddie, do you have 188, 11?
6 over 7.
All in favor? Okay, to Freddie B,
5 over 14.
all in favor?
4 over 7.
Senior or female? Oh, be careful about what you haven't counted yet. So how many seniors are there? 10 seniors, agreed?
Seniors.
And how
Yes.
many females haven't you counted yet?
I
6.
missed the ABC thing.
Okay, working that. So everybody do B, see what new answers we get. A senior or a female? Tony, your new fraction is
I have 4 sevens.
16 over 28. I also have 4 sevens. 16 over 28. So let's approach it in steps. So Freddie, how many seniors are there?
10.
And how many are female juniors are there?
Female juniors.
Right.
Six.
6, right.
Yeah.
So a total of 16 favorable. And how many total students are there?
28.
Okay, 16 over 28, right answer. Well done. So Hannah, number C, a
One.
junior or a senior?
1.
1, well done. Tough problem. Okay. Now, number 12, answer to A. So Freddie, you have an answer to 12A.
1/2.
All in favor? Carries. Hannah, B.
20 over 260, so 10 over 13.
All in favor?
Yes.
Good. And C, please, Tony.
8 over 13.
All in favor? Well done, guys. So on the next problem, number 19, hi,
Oh, we're supposed to do 19, Brody?
it's in the assignment sheet,
Is it?
okay? The frequency distribution and, is given, and A, that has exactly 2 tests done. Hannah, exactly 2.
1 out
Probability.
of 15.
1 out of 15,
Yeah, I couldn't see that.
okay, those are actually readable.
Number
So-
19 on page.
188. So Tony,
Okay, yeah, I didn't, for some, yeah, I
okay,
didn't do
so
that one.
Tony, what about B? At least 2 tests.
1/3.
1/3, all in favor? 1/3, okay. C, Hannah, at least, at most 3 tests.
5, 6.
All in favor? Good. And D, Hannah, has 3 or fewer tests done.
5, 6. Oh, 3 or fewer.
3 or fewer.
It's like the same question. Right?
At most 3, 3 or fewer. Sure looks like the same question to me.
Yeah.
Okay, should have same answer. Okay, and Tony, the last one, 1 or 2 tests done.
1/3.
All in favor? 1 or 2 tests. 10 over 30, 1/3. Okay, so we did manage to do that. And now we can look at page 189, which is Xerox challenge also. Number 20 is out of the question. 21 is out of the question. And
I didn't do these.
I wouldn't either, there's no
Oh,
19.
I did those.
You did those? 20
I
and
did
21?
20, I couldn't
I
write
did 20 and
21.
21.
Well,
It
interesting.
doesn't mean that they're right, because you
Okay,
can't really
that's
read them very
okay.
well, but
You were able to read it? Okay, so Tony, 21A, your answer is,
1/20, 1 over 20,
and 21B,
17 over 40,
21C,
9 over 40,
and 21D.
5 over 8.
Okay, they've been recorded. And the next problem is 20. Did 20 get done? Yes?
Yes.
So the next problem is 19, which is a misprint because we've already done it. There's no new 19. So we've done those as best we could given the Xerox situation. And we now proceed to page 656. Page 656. So Freddie, could you get us started with number 3?
I got 136.
Well done. Freddie, you're on a roll. Number 4,
1 over 6.
Oh.
No?
crash and burn. We want red and red again. So, what's the probability of a red?
It's 3 out of 6.
1/2, agreed?
Yeah, 1/2.
So what's the probability of one red followed by another red?
It'll be 1/4.
That's right.
Okay.
Okay.
You just divide it. It's half the probability. You did it
Exactly,
twice.
exactly, exactly.
So probability gets cut in half.
Exactly, you understand it conceptually perfectly. And so 5, please, Tony,
1/4,
7, Tony,
1/36.
8, Tony,
1/12.
9, Hannah,
1/8.
perfect, 11, Hannah,
1/36.
and 13, Hannah,
1/3.
good, 14, Freddie, please,
1/6,
good, and 16, Freddie,
152,
perfect, 17, Freddie,
1/169,
guys are good, 19, please, Tony,
1/4.
what do we even do this, 23, Tony,
1/6.
uh-oh,
that's what I got,
oh, 20,
3.
oops, wrong point, 1/6, my bad. Okay, wrong problem. Now, the next one is similar to the one that we did. So, we're gonna get ready for it. About 30 seconds here. Getting set up. Section 11.7, number 25. So, A, Hannah.
1/256.
So winner. B, Hannah.
1/4096.
Good. And C, Hannah.
15/16 to the 10th power, so 52.4%.
52.4%, it's excellent. And take us out, please, Hannah, with D.
1 minus 15/16 to the 10th power, which gives me 47.5%.
Perfect all around, extremely well done, problem. 25, and next comes 26. So, Tony, 26A,
1/100.
Tony B,
1/1000.
and C,
34.87%.
good, and D,
65.13%.
okay, another well done.
What'd you get for D?
65.13%.
It's 1 minus C, it's 1 minus C, so this also well done. Okay, now we get to some that are going to be a little bit more tricky. Alright, so our next one is, I believe 36, am I right?
33.
33, not even close. Okay. Good, this is, stuff that actually should be done experimentally. I mean, you should get the chocolates, eat them, and count.
I didn't bring any here. I didn't want to tell you.
Okay, well then we'll just do it theoretically. So, Freddie, 33,
I got 1/60 now. I know I probably did these wrong.
okay, well, let's do 2 solid chocolates in a row. So how many total chocolates are there?
15?
30, tells you, there are 30 chocolates in the box.
Oh, yeah, I got it, I wrote it down.
And how many are solid chocolates? 15.
15.
So this is just what you did before, 1/2 times 1/2. Oops, that's wrong, 2 solid, oh, because it reduces. It's not, because it's not replacement. Okay, so what's the probability of the first chocolate? I would suggest it's 15/30. Do you agree to that? There's 15 solid chocolates. So the probability of A times B equals the probability of A times the probability of B given A. Now, the probability of the first chocolate is 15/30. 30 total chocolates, 15 solids. We okay on that? So if you do get a chocolate on the first one and you reach for the second one, then what's the probability of the second item being a chocolate? First one's gone now, right? So how many total are left in the box? The box
29.
29. And of those left in the box, how many are favorable? Okay. So Tony, the numerical answer is?
7/29.
Good. Now we do exactly the same kind of calculation for 35, only the numerator is not decremented. So Hannah, what do you have for 35?
5/87.
All in favor, 5/87. So Freddie, are you okay on 35?
Yeah.
Okay, good. And 36, please, Freddie, you have an answer for 36?
I got 2/3, but I know that's wrong.
Okay, so you're gonna change your strategy on these. Tony, your answer,
5/58.
and we have a winner there. Okay, now they get harder. 37, Tony, you have two Democrats.
2/21.
Okay. And 39, Freddie, you have 39, an independent and then a Republican.
This is supposed to be 4/35?
Well done. Freddie, you're on a roll, 40.
I know that's wrong, 3/5.
You're right, it's wrong. Okay, first let's take it in two places. What's the probability of getting an independent? Anybody?
4/15.
4/15. Followed by a Democrat. What's the probability of a Democrat on the second hit?
5/14.
5/14.
Oh.
One guy's gone.
That's right.
That's right, gotta kick that down.
Mm.
So, Tony, the final numerical answer is?
2/21.
Okay, we have a winner.
I see what I did. I
Yeah.
was not subtracting. Yeah.
Right. Okay, no independence. Hannah?
11/15, I may have jacked that up.
Yeah, you want to re-examine that. No independence. Everyone want to redo number 41?
The answer's supposed to be 11/21, right?
Yeah, how'd you know that?
I don't know, probably in the back somewhere. I don't
Well,
know.
nothing wrong with that. 11/21. Tony, you calculated that? 11/21. Let's all calculate it. No independence. So the first selection is 11/30. Next selection is 10/29.
And 15 and 14.
Yes, right. Okay, 11/15 and 10/14. I'm still eating chocolates.
You're always in chocolate.
Okay, so we're okay on 41 now. And next is 45. These are tricky. Hannah, 45. Your answer is?
8/855.
All in
That's what I
favor?
got.
All right. Guys can drink. 46, Freddie.
9/10.
Nope, because you gotta decrement the bottom. A can of apple juice.
6.
Okay, now how many total cans are there?
20.
So the first one is 6/20.
Right.
Next, a can of grape juice. How many grape juices are there?
8.
So it's 8/.
19.
Good. And a can of orange juice, how many orange juices?
4/18. Right. Should
I
be.
think, yeah, 4/18, all in
Yeah,
favor.
I didn't subtract the
That's why we do this. So, Tony, the final numerical answer for 46 is?
24/855.
Reduces to 8/285,
Oh.
I hope.
I was just testing you.
So what is it?
How detestable. Okay, now the hard one. 47, the killer. No grape juice. Not an easy problem. No grape juice. It's hard to live without grape juice. Okay, Tony, your answer to 47 is?
11/57.
Hannah, your answer is?
11/57.
Freddie, your answer is? Should be 11/57.
11/57.
Sure is. Okay, well done. 51.
We stopped at 47.
Yeah, you told us to start with 47.
Okay, please complete for,
Yep. You said start with
Class.
47.
I wonder if there's any more to present. Yes, there was, because we didn't tell you about givens at that point. Now
Right.
you understand givens, so you can complete. And we only have, one section to continue presenting. You guys are on track to get out early. I don't know if you
I hope
can
so.
handle that or not. I'll try to find some extra material.
I can go home and work on my psychology presentation.
I can sit here and work on my history.
Well, yeah. Or I can sit
No,
here
I
and
really know I'm going to find some extra material. Working on other courses.
How dare we?
And you told us we could use tutoring for that.
2 to 4.
It's a quiet environment here.
I don't go home with them, it's just a waste of gasoline.
Amen? Okay, section 11.8. We enter a whole new world, we cross the line. Nothing is going to be like it was before. This is not Kansas anymore. What jokes? What jokes? Okay, 11.8. Now, what we're doing at this point is changing the course from the first half to the second half. The first half of the course was on descriptive statistics, where we took a data set and we squeezed out of it as many calculations as we could. And they were all known to be true because the data was known to be true. They were fixed. There was no guessing. They were all 100% accurately calculated and believable. Now we're going to infer things about the present. Inferential statistics, loosely called infernal statistics, but that's personality. And the first switch that we're going to make is if you have an existing data set, then it's easy for you to talk about the mean of that data set. That's a very real number. Okay? But if you're talking about the future, then what you're talking about is the probability of a certain occurrence. The probability of a certain occurrence. So now, if I take this die and I throw it, what is the probability of getting a 6?
1 out of 6.
1/6. What's the probability of getting a 5?
1 out of 6.
So I can make what's called a probability distribution. This is the value that I'm talking about. 1, 2, 3, 4, 5, or 6 dots. And this is the probability of getting that particular value. And they're all the same, true? So now, I'm going to ask the question and introduce a new term to you. It's called the expected value. If I roll this die right now, what is the expected number of dots to occur? What value of dots can you expect to occur? No, but if there's only one okay, I'm going to throw this die. Okay. Now, my hand is over it, you can't see it. I want you to tell me how many dots you expect to see if I lift my hand. How many dots you expect to see?
4.
A range,
There is an expected value, and the expected value is calculated as the sum of x times the probability of x. So what you have to do is take a new column.
okay. 6 times 1/6.
That's right. That's going to be touchy. Not sure why that doesn't work. But it sure doesn't. And it's not over here, so I have to erase it the old-fashioned way. So I'm going to make a new column, which is called x times px. And I'm going to populate it. And the first one is 1 times 1/6, 2 times 1/6, 3 times 1/6, 4 times 1/6, and 5 times 1/6. Okay, so this is equal to 1/6, 2/6, 3/6, 4/6, 5/6. So I've added them all up. The sum of x dot px is equal to 9, 12, 14, 15, 6, which is equal to 3 1/2. So the number of dots you expect to see when I raise my hand is 3 1/2 dots. But you say that's not a possible number. The expected value doesn't have to be a possible number. It just has to be the number that you expect to happen.
Is that kinda like the mean of
It's
6,000?
exactly equivalent to the mean. It's exactly equivalent to the mean. And to verify that it is exactly equivalent to the mean, I want you to tell me what is the mean number of dots that you will see. So you add up all of those dots and divide by 6. Go ahead and add up all of those dots and divide by 6. 11, 15, and 6, 22.
3.5.
3.5, same, agreed? Okay. Did something wrong over there. So this is 22 over 6. 21 over 6. Right. 21 over 6 equals 3.5. And I added up this column a little hastily because I didn't include the number 6. 6 over 6. So this is also 21 over 6. 3.5. Okay, now, the basic statistic principle that we are looking at here is the average of the past is the expected value of the future. The average of the past is the expected value of the future. The average number of dots that are going to appear rolling this die is 3.5. So if I roll the die in the future, I expect to see that many dots. It's not a possible value even for an average. So let's go to our second application. This one is done for you at the page 659 at the bottom. We calculate the expected value for a die. So let's turn the page and go to a more real life situation. Let me give you a Misawa Air Base situation. What we're going to do is to look at 10 families, and this is the number of children that they have. 0, 1, 1, 2, 2, 2, this is 6, 3, 3, 7, 8, 9, and 10. 10. So n equals 10. Okay? N equals 10. What's the average number of children in the Misawa Air Base family? The average number of children. Sorry? 2.3. They say that's ridiculous. There's no family that has 2.3 children. No, it doesn't have, the average doesn't have to be represented. It's an average number for the data set. Now, I'm going to form a new problem. So the n equals 10, agreed? So now I'm going to make a new data set. 0, 1, 2, 3, 4, and 5. Now, if I choose one of these families at random, what's the probability that I have chosen a family with no children? Why is it 1/10? Because how many total families are there? 10. How many are favorable to having 0 children? 1. So the probability of choosing a family with 0 children is 1/10. What's the probability of choosing a family with 2 children? With 1 children? 2/10. What's the probability of choosing a family with 2 children?
3/10.
3/10. And the probability of choosing a family with 3 children? 2/10. And we finish off with 1/10 and 1/10. Now, if I add up this column, what am I obligated to get? 1. Because if I choose a family, I will choose a family somewhere in the data set with certain probability. So the probability of choosing a member of the sample set always totals to 1. Doesn't read this add up to 10 over 10? So we have that. Now I'm going to make a new column, x dot px. 0, 2 tenths, 6 tenths, 6 tenths, 4 tenths, and 5 tenths. And I'm going to sum this column. And please tell me what you get when you sum that column.
1/3 over 10.
Oh, also known as 2.3, agreed? Now, when we took the average of the data set, what number did we get?
2.23.
When we took the expected value, what number did we get? So the expected value of the future is the average of the past. So what this means in words is that, suppose a new family with no children comes to Massawa to live, and they start to have their family. You can now tell them with confidence, you are expected to have 2.3 children. That's your expected number of children, is 2.3. Because that's the average value of all the other families on this base. So it's the value that you are expected to also have. Agreed? So the expected value represents a hypothetical average of the past projected into the future. So if a new family comes with no children, or a couple gets married here, and they say, how many children can we expect to have? You say, well, based on the fact that you're at Massawa, and the average number of kids at Massawa is 2.3, then your expected number of children is 2.3. So expected value is related to the average of the past.
You just multiplied across on the
I've
numerator.
just multiplied across. Not a hard course. So let's go to example number 2. Now we're going to have a family with 3 children. One family with 3 children. And we want the expected value for the number of girls for a family with 3 children. Now we have looked at the these probabilities before. So please refer back to page 627. Refer back to page 627. In the lower right-hand corner, you have a list of all of the 3-child families you can have. 627.
It's in the old packet.
It's in the old packet, sorry about that.
Oh,
Okay, good. So how many total different families can you have with 3 children? How many different families?
8.
8, okay. Now, how many of those are favorable to having no girls? 1. So what's the probability of having a family with 1 girl? I think it would be 1 over 8, agreed? With no girls. So we have x and p of x. So no girls was 1/8. What's the probability of a family with 1 girl?
3 over 8.
And the probability of a family with 2 girls?
3 over 8.
And the probability of a family with 3 girls?
1 over 8.
Good. Okay, now the same, we hold a new column, x dot px, and the sum of this column is our expected value that we're looking for. So make your new column and sum it up, and you find the expected value for the problem that we're now working on way up in 11.8. So we can go back to our 11.8 page, where he does exactly the same thing. And what is the expected number of girls?
One and a half.
1.5 girls. So if you're gonna have 3 children, you can expect to have 1.5 girls. I didn't say this was a biological course, it's a statistical course. Now, these expected values have a widespread application in the real world. And this is our first very real application. So let's read example 3 at the bottom of this page very carefully. Page 660, example 3. This is a real life application. An automobile insurance company has determined the probabilities for various claim amounts for drivers age 16 through 21 shown in the table in the margin. Okay. So let's be sure we understand to read this table. So Freddie, what's the probability that an insured driver will not make a claim? Claim $0.
0.7?
70%. What's the probability that the claim will be 2,000?
0.15?
Good. And Tony, what's the probability that the claim will be 10,000?
1%.
Right. Now, when you have a column of X and PX, can you not make a new column, X dot PX? And if you sum that, you can get the expected claim. The expected claim of the next driver you insure. The next driver you insure, you can expect to make a claim of the expected value. So let's make a new column, X dot PX. So X and PX, 0.7, 2,000, 0.15, 4,000, 0.08. 6,000, 0.05, and 8,000, 0.01, and 10,000, 0.01. So let's make a new column, X dot PX. So we've added 0, and I believe 300,
Yes.
and the next number is 240.
320?
320, next number is another 300,
Yes.
and then an 80,
Yes.
and a 100.
Yes.
So if we sum these up, we can get the expected claim of a new person that we insure. So if a guy comes in the office tomorrow and buys an insurance policy, we can expect that he will end up claiming this amount of money. So what do they sum to? 1,100. Now, as a business, if this new person comes into the office tomorrow to buy insurance, and you expect him to ultimately make a claim for $1,100, what are you going to charge him for his premium?
Way more than that.
At least that, let's hope, agreed? Are you a good business person if you only charge him $500? No, because it's expected that he's going to claim $1,100 from you, agreed? So that's what expected value does. It permits you to determine statistically what you should be charging for this premium. Okay? At the very least. Now, example 4 is very complicated, so it's going to take you a few minutes to read it. It's a very thorough, real-life example of how to apply expected value and make a realistic business decision. So go ahead, read it through until you're totally confused, and then we'll try to unravel it. took me 3 readings before I could piece this one together. Tony, can you explain this problem to me?
So basically, I feel like the first half of it is not really, but, so basically, they wanna know if selling the house obviously is worth me doing it myself, so I want to know if what I'm going to make versus what it's going to cost me to do it, if it's going to be worth it.
Yeah, what I
Only
expect to
it's
make, the
$6,000.
expected value, there's no certainty. That's good. Okay, now, there's three possible outcomes. First, he cannot sell the house. Nothing works, agreed? So if he doesn't sell the house at all, then what is the amount of money that he gains? Answer minus 5,000. Why?
Because that's what it cost him
To try to sell the house. It cost him $5,000 to try to sell the house. That's why he's considering not taking the listing at all, because he's got to invest $5,000 in cookies and beer for his showings. Okay, so he shows the house, and if he sells it himself, then how much commission does he get?
$30,000.
$30,000, agreed? Now, he can also open the sales to his fellow real estate agents. Give them a green light to also try to sell the house. It's his listing. But if he says, you guys try to sell the house, and if you do sell the house, then you're going to give me part of what you made, agreed? So if another agent sells the house, what does the other agent have to give him? How much? $15,000, right. So now we can make what's known as a probability distribution. We can make gain or loss with the probability. Actually just gain, and the probability of that gain. So in real words, he sells the house. If he sells the house, how much did he gain? 25,000. Why not 30? Because he had to buy the cookies, right?
Advertise.
Yeah, all that stuff. So he gained 25,000. The probability of him selling a house is 0.3. Now, if his friend sells the house, the agents don't have friends. If a fellow agent sold the house, then what's his gain?
10.
10,000. And what's the probability of that happening? 0.2. Now, if he doesn't, if nobody sells the house, then his gain is minus 5,000, agreed? And what's the probability of that is 0.5. So we need to make a new column.
So is this under the assumption that he's going to pay the $5,000
Oh, yes.
regardless?
Oh, yes, that's the
Okay.
rules. That's the rules.
Okay.
But he has to do the advertising and the cookies and beer. As soon as he decides to take the listing, he is obligated for promotion.
Okay.
So now let's make our new column, x.px. And let's populate it. What is 0.3 times 25,000?
10,500.
And what is 0.2 times 10,000?
2,000.
Good. All those are pluses. Now what is 0.5 times minus 5,000? So that's a new column. And the sum of that column is the expected outcome. The sum of P dot X is the expected outcome. So what is the sum of that column? $7,000. So, his expected outcome is $7,000, and there's one more factor in his decision, and that is he's not going to invest his time unless he can make at least what? 6,000. So this expected value analysis tells him very clearly what to do. So Freddie, should he go for it?
Yeah, I mean, he's only making 1,000 over the minimum
Well,
6,000,
once again,
but he
this
still
is only
works.
an expected value. It's
So,
a
yeah.
guideline. He could
So
bust.
he can do it.
So, it's a guideline, it's better than nothing. Just turn the page, go to our next type of problem. Example 5. A game is played using one die. If the die is rolled and shows 1, 2, or 3, the player wins nothing. If the die shows 4 or 5, the player wins $3. If the die shows 6, the player wins $9. But you have to play $1 to play the game. So what can you expect to happen? Let's take our probability distribution table. So this is a probability distribution table. Because it's a probability distribution. So, if X is equal to 1, 2, or 3, no, if the die is equal to 1, 2, or 3, this is a case. 1, 2, or 3, then what is the gain? -1, because you pay $1 to play the game, and you don't get any winnings. So you see why it's a -1. That's your outcome. You lost. So you don't just walk away, they keep the $1 that you paid to play the game. But if it's a 4 or 5, then what is your gain? Well, they give you $3. But you already paid $1 to play the game, so what's your gain? $2. Now, if the outcome is a 6, they give you $9, but you've already paid $1 to play the game, so your winnings is $8. Now, what's the probability of X in each case? You tell me, you know all about die. So what's the probability of a 1, 2, or 3? 3 over 6. What's the probability of a 4 or 5? And the probability of a 6. Does this column always have to add up to 1?
Yes.
If it doesn't, it's not a probability distribution, and you can't use this. Now we create our X dot PX column. So what is this column? Minus 3, 6. This is 4, 6. And this is 8, 6. So our expected value is the sum of this column. So it's 12, 6 minus 3, 6, or 9, 6 equals $1.50. Should you play this game? Should you play this game? Freddie, would you play this game? Every time you play the game, you're expected to gain $1.50.
Yeah, because I'm still 50 cents up.
No, the dollar's already included. You gain. That's your gain. The dollar's already been subtracted off. You've gained $11.50, $1.50, okay? So every time you play the game, you gain $1.50. That's a positive expected value, true? You just play this game all day long. All day long you should play this game. Is this real life game? It's a dream game, okay? Now, sometimes you win, sometimes you lose, but the expected value comes in if you play the game a large number of times. It will turn out to be reality. So if you play this game 1,000 times, you can then walk away with $1,500. But if you play it once or twice, you could just keep losing. But over a large number of times, the expected value turns out to be what actually happens over a large number of times. Now, the next one is roulette. Roulette is an interesting game. It's played in the Las Vegas casinos. And a ball is dropped onto a spinning wheel. The wheel has buckets on it where the ball can land. How many of you know what a roulette spin looks like?
Seen it.
Seen it, okay, you've seen it? At
Yeah,
least
I
in a
haven't done
movie?
it, yeah, I've seen it.
Good, okay. Now, how many buckets are there in the wheel? There are 38 buckets. The buckets have the numbers 1 through 36, and the number 0 and 00. Okay. So let's say that you bet on the number 17 coming up, the ball going into the bucket 17. Okay. So you bet on the bucket 17. So what's the probability that that ball will land in bucket 17?
1 over 36 or 38?
1 over 38. So the probability of 17 equals 1 over 38. Agreed? So it stands to reason that if you bet $1, then the house should match that with $37. And we'll talk about odds in a moment. Okay. So that would be a fair game if they paid you according to the probability. But the casino is not there to break even. The casino is there to make a profit. So if you win, they don't pay you the $37 they should, they pay you just $35. And the difference is where the casino makes its money. Okay? So I want to clear this up by going back and covering a topic that I deferred just in case we had time for it. And we do have time for it. So now we're going to learn what odds are. And the page to go back to in the previous handout, would be somewhere in 11.6. You find the topic of odds. Page 643. Page 643, odds. In the previous handout. Or is it on this one? It's on this one.
It's 643.
Yeah, it's this one, yeah. Okay, so smile if you found page 643. Good enough. Okay, now, the probability of A happening is the number of favorable cases over the number of total cases. Now, the odds of A are the number of favorable cases over the number of unfavorable cases. So you see, it's a related but slightly different topic. So I'm going to give you a real life example. You go down to the racetrack and there are 8 horses running. 8 horses running. So you pick your horse and you bet $1. Now what's the probability that you're going to win?
1 out of 8.
1 out of 8, agreed? Now, what are the odds against you? 7 to 1. Because the odds are the number of unfavorable cases compared to your favorable cases, agreed? So the odds are 7 to 1. The probability is 1/8. But in gambling, you use odds. So the odds are 7 to 1, okay? Now, if I pick a card out of this deck, what's the probability that this is a club? Probability,
13/52.
1/4, 1/4, agreed? But what are the odds against it being a club?
4 to 1.
3 to 1.
3 to 1.
3 to 1 odds against it being a club, right? So we had a riverboat gambler in the old days. The year was 1857. I warned everybody they wouldn't listen. He left the riverboat, he went into a small farming town on a Saturday afternoon. And a young farm lad just had his salary given to him, went into town. The gambler laid a deck of cards on the table, said, I'm going to give you a chance to make some money. Says, tell you what I'm going to do. You put $1 on the table. And if you pick a card, if it's a club, I'm going to give you your $1 and $2 back, plus. But if it's not a club, I'm just going to take your $1. Now that doesn't sound like something you should be doing. If you win $2. If you lose, you only lose $1. So where's the catch?
Did you see the deck of cards beforehand?
No, no. The money is at 2 to 1, isn't it? 2 to 1 is the money. He's giving him twice the money if he wins and taking 1 if he loses, true? But what are the actual odds against, the actual odds against winning are 3 to 1, aren't they? He can draw a diamond, heart, or spade, and he loses. That's 3 cases that he can lose, agreed? Only 1 that he can win. So the odds against him winning are 3 to 1. But if he wins, the payoff is only 2 to 1. So sure, he's going to win some of the time. Gambler gives him $2, doesn't mind at all. Because at the end of the day, who's going to have all the money? The gambler is, because the payoff odds are not the same as the actual odds. The payoff odds are not the same as the actual odds. And that's where gamblers make their money, on that slight difference. Now, why are odds used in gambling and not probability? The answer is that they make handling the money very easy. At the racetrack, if the odds are 7 to 1 against you, you put $1 on the table, the racetrack puts $7. Winner takes it. Okay? You do a football game, betting. The odds are 17 to 12. 17 to 12 against you, agreed? So you put $12 on the table, the other person puts how much? 17, winner takes it. So odds make counting the money very easy. That's why odds are used in gambling. But when there's a difference between the actual odds and the payoff odds, then it's not a fair game. So let's look at this roulette wheel that goes around. It's got 38 buckets. And the buckets are 0, 00, and 1 through 36. Or 38 buckets, agreed? Now, if you bet $1 that the number 17 is going to win, then what are the odds against you winning? 37 to 1, agreed? So in a fair game, you would put $1 on the table, and the house would put $37 on the table, agreed? Winner takes it all. But you put $1 on the table, and then the house gives you your dollar back, but they only give you $35, not 37. So the payoff odds are 35 to 1. Actual odds, 37 to 1. You don't much care because you get $35. But the reason that this is true is because if this wasn't true, then the casino wouldn't be there. Now, when you win a lot of money at Las Vegas, does the casino mind? Does it upset the casino if you win a lot of money gambling? They don't mind at all, because you're not winning their money, you're just winning some loser's money. They make their money on this slight difference between the payoff odds and actual odds. Every time the wheel spins, the actual odds are 37 to 1, they only pay off 35 to 1, and that slight 1 or 2% difference is where they make their money.
Because of the zero and the double zero
Yeah,
spots, right?
that's how it's put out there in the wheel, so it looks like it's 35 to 1. But, when you win the money that the other players lost. The house makes the money by not paying out quite as much as the actual odds. So every time the wheel spins, the house makes 1%. So the house doesn't care who wins and who loses, the house just cares how many times the wheel spins. That's why they have free drinks, free rooms, and all the shows. Because the more times the wheel spins, the more money they make, because they make their money on the slight percentage difference between the actual odds and the payoff odds. So they just want to see the game played and played and played. And every time it's played, they make a small percentage. So when somebody loses a lot of money, they don't lose it to the house, it goes to the winners. And the house just taps a little percent. And the mechanism that they use for tapping is the difference between the actual odds and the payoff odds. So let's go back to our expected value. Back to 11.8. And page 663, expected value and roulette. One way to bet in roulette is to place $1 in a single number. If the ball lands on that number, you're awarded $35. Are those the actual odds? What should you be awarded?
37.
Yeah, but you're not, because the house needs to skim. That's where they get theirs from. So you get $35, you get to keep the dollar. If the ball lands in any other, 37 slots. Notice 37 slots, not 35 slots. That's the catch right there. So you find the expected value. What's going to happen to you? So you make your probability distribution table. You bet on the number 20. And if it lands on 20, you get the money on the table. You put $1 on the table, they put $35 on the table, so you get your dollar back plus 35, so your gain is $35. But what's the probability of that happening? 1 over 38, agreed? 1 over 38, not 1 over 36. So, if it doesn't land on 20, you lose your dollar. And what's the probability of that happening? Okay, so now make your next column. The expected value is X times the probability. So it's $35 times 1 over 38 minus $1 times 37 over 38. So you expect to have what happen every time you play? You expect to lose a nickel, agreed? Every time you play. Let's put it in the reverse direction. The house expects to win a nickel every time you play, agreed? And that's where they make more money, a nickel at a time. Every time the wheel rolls for a player, they make another nickel. And it all adds up. So the expected value in roulette, when you bet on a single number, is minus 5 cents. So now, in all games of chance that are run, for somebody to earn a livelihood, your expected value will be negative. Because that's why they run the business. But you want to keep it as small as possible, agreed? So you can expect that your expected value is going to be negative. But that's only your expected value in the long run. In the short run, you can win big, agreed? That's why people play. They want to just win big in the short run, okay? So that's why in the previous game of chance, where we had an expected value that was positive, then the house is ultimately going to go out of business, aren't they? So that's the one you want to play all day long. Okay, I'd like to have you guys give yourself a pat on the back, congratulate you because you're out of here 7 minutes early.
Couldn't somebody theoretically like watch other people play for like 4 hours or whatever and be like, take note of the numbers they didn't hit yet and then increase your chances of when they play,
There's
they
no
get over there
carryover.
and then they
There's no carryover,
okay.
and I tried it myself.
I was just wondering, well, I don't know, I'm not a gambler, I was just wondering like.
You shouldn't be if you
people
say
do
that. Okay, now I'm gonna toss this coin, and I get a head. What was the probability of that?
One to one.
But now I'm gonna toss it again. What's the probability of getting a head on the next one?
1-4?
No, 1/2 again, there's no carryover.
Oh, okay.
In fact, you know that, because you can go outside the room. When you come back, I'm not gonna tell you if I tossed the coin before or not. You're just gonna see me toss it for the first time. Every time you toss the coin, there's no carryover. So it doesn't matter what happened before.
If it was 2 coins, it would have been,
No,
if you,
so unless you're talking about the probability of getting 2 heads in a row, there's no
That's
Yeah,
carryover.
different,
yeah.
that's right.
yeah,
That's a different bet.
Yeah.
But if you're betting on them one at a time, there's no carryover. And I went to Vegas to try it, just as you suggested.
How much money did you lose?
I was lucky, because I had this plan that I was going to bet on a 50-50 game, toss a coin, and if I won, I was gonna put my money in my pocket, and I was gonna bet the same amount the next time. If I won, I put my money in the pocket, bet the same amount next time. If I lost, the next time I was gonna double my money. So that I would, if I won, then I would pay for the loss before. If I lost 2 in a row, I was going to triple my money. So eventually I knew I would win, right? Well, that's what I said. Eventually I know I would win, and when I win, I'm gonna pay for the whole string of previous losses and still have another win. It's called the double up method. And so I said, well, I went to Vegas with enough money to be able to handle 8 losses in a row. Because I said, it's never gonna lose 8 times in a row. Because the probability of that's 1/2 to the 8th power, agreed? Okay, so I walked in and I said, well, I got my money, I'm ready to play. But just before I started to play, I said, I think I'll watch for a while. I watched 9 straight losses. And my money stayed in my pocket, because there's no carryover.
Only bet what you wanna lose.
Yeah, but only lose what you can afford to lose. Okay, so class is on Tuesday. Okay. Okay, we're done. Thank you very much.
Did you order homework?
Negative, keep your homework until after the next test. You'll need it to prepare for the next test on.
The A1 to A4?
At one day 4, I'll take any old time, today or any other time. Yeah, and this looks like a stapler, but it's actually a homework collection point. So you can just, okay, just
We
put it
have
on
this
the
conversation.
stapler.
Yep.
That's at home.
Okay, next time.
A1 to A3 stuff.
Okay, just be sure to label A1, A2, and A3 at the top of the appropriate pages.
And I changed how I was doing it to make it easier next time.
I feel better. I feel so much better.
I know that it takes a week usually, but I'm just curious because I'm so anxious to know. Have you
No, I
started
haven't
grading?
graded them yet. My best grading day is Sunday,
Oh,
so there's a chance for Tuesday.
I knew I should have brought cookies today.
There's a good chance for Tuesday.
Should have brought cookies to Brandon
Cookies,
before,
why shouldn't
before he
you
started grading.
Cause then he would've been like, oh, I should sit down and grade and eat these delicious cookies. And then.
Yeah.
I
He'd
gave you
be
all
in
the
a good
chocolate,
mood
I
while
have
he
no
was
bribing
grading.
left. I'm kinda busy.
It weakened me, it weakened me, I'll tell you that.
The snark will be forgotten while you're grading.
Oh, that's bad.
Alright, thank you.
Okay, see you Tuesday.
I get whatever grade I deserve, so.
You said you know a lot about quantum physics?
I don't
Quantum
know a lot
mechanics?
about quantum physics, I studied it. Yeah, I've studied
Very interesting, huh?
it. It is, it's fascinating.
It's a good book,